Hello, welcome to Chapter 8, Sampling Distribution of Sample Proportions, Hypothesis Testing. In Chapter 7, we saw that under certain conditions, the sampling distribution of sample proportions follows a normal model whose mean is the proportion in the population and whose standard error is given by this formula. We also saw how to use this model to build a confidence interval for one proportion and for the difference between two proportions. In this Chapter 8, we will use the same mathematical model to test a hypothesis also about one proportion or about two proportions. We will introduce the p-value, which is usually considered a measure of strength, likelihood, or compatibility. This chapter should be easy if you have fully understood the previous one, because the mathematical part is similar and the procedure has fewer steps. Here you have the main new concepts that we see in this chapter. I will introduce them as we go over the exercises. Exercise 1. We suspect that a coin is loaded in favor of heads. To test this hypothesis, we toss it 100 times. Consider the results shown in the following scenarios. Scenario A, 54 heads and 46 tails. Scenario B, 71 heads and 29 tails. Question A. Does scenario A provide strong evidence that the coin is loaded in favor of heads? Why? Students usually answer no, and they explain it very well. They say that if the coin is fair, in theory we should get 50 heads and 50 tails. Since this outcome is similar to that, there is nothing suspicious here. I am phrasing this answer here in more proper terms. No, there is no evidence that the coin is loaded in favor of heads. In a fair coin, the expected number of heads in 100 trials is 50. The 54 heads observed in our sample are not too far from that. The positive difference of 4 heads could very well be explained by the natural variability of the tossing, that's to say, by chance. Question B. Does scenario B provide strong evidence that the coin is loaded in favor of heads? Why? Students also answer this very quickly and very nicely. They say that since this outcome is very different from the theory, this is very suspicious. They call it the theory. They mean to say the expected value. That's the proper term, because the theory also says that samples vary. So a proper answer would be, yes, scenario B provides strong evidence that the coin favors heads. In a fair coin, the expected number of heads in 100 trials is 50. The 71 heads observed in the sample are too far from that. It's not reasonable to believe that such a big difference could be explained by the natural variability of the tossing, that's to say, by chance. Notice that you can answer these two questions very nicely without any mathematical calculation, just by applying common sense. The problem with common sense is that it is not objective and it doesn't work well in gray areas. For example, what about scenario C, 60 heads and 40 tails? Here, there is never agreement among students. Some say that this is pretty much the same as scenario A, just 6 heads more, so nothing suspicious. And some say that this is very suspicious because we have 10 heads more than expected. To try to clarify this with numbers, let's answer question D. Let's consider the possibility that the coin is fair. If it is, calculate for each scenario the probability of getting in 100 tosses of the coin a result as extreme as or more extreme than the result in that scenario. Use the binomial model. In scenario A, we observed 54 heads. What's the probability of observing so many heads or even more heads if it is true that the coin is fair? That's to say that the probability of heads is 0.5. The binomial calculator will tell you that in a binomial model with 100 trials and a probability of success 0.5, the probability of getting 54 or more successes is 0.242. This probability confirms your intuition. There is nothing suspicious in this scenario A, because with a fair coin, almost 1/4 of the time, we will see a result like this or even more extreme than this. It's like if you have 4 cards, one is an ace, 3 are jokers, you pick one randomly, and it is the ace. Not very surprising. Scenario B. What's the probability of getting 71 heads or more than 71 heads in 100 trials if the coin is fair? According to the binomial model, this probability is 0.00001608. This probability also confirms your intuition. We have very strong evidence that the coin favors heads, because if it didn't, this outcome would be virtually impossible. Scenario C. What's the probability of 60 heads or more than 60 heads if the coin is fair? 0.028. This probability also confirms that this scenario is a gray area. This is not likely at all, but it's not inconceivable either. What do we do here? A student mentioned that we should use some sort of level of tolerance, and I totally agree with that. If you have understood that these probabilities are useful to make a judgment about the fairness of the coin, we are ready to introduce the vocabulary. In this example, we have two hypotheses, one that says that the coin is fair and other that says that the coin favors heads. The one that can be expressed with an equality is usually called the null hypothesis, denoted H subscript 0. In this case, it is the hypothesis of the coin being fair, because that can be expressed as probability of heads equals 0.5. The hypothesis that can be expressed with an inequality is usually called the alternative hypothesis, denoted H subscript A. In this case, the alternative hypothesis is the probability of heads is greater than 0.5, or equivalently, the coin favors heads. This probability that we got here, or here, or here, is called the p-value. It is usually considered a measure of compatibility between the null hypothesis and the observed data. How compatible is an observation of 54 heads with the idea of the coin being fair? Fairly compatible. How compatible is an observation of 71 heads with the idea of the coin being fair? Not compatible at all. Almost zero compatibility. This observation contradicts or discredits very much the null hypothesis. How compatible is an observation of 60 heads with the idea of the coin being fair? Not very compatible, very little compatibility, but still plausible. The p-value is also understood as a measure of likelihood. How likely is it that the null hypothesis is true? In scenario A, how likely is it that the coin is fair? Fairly likely. And here, not very likely. And here, not likely at all. It is also interpreted as a measure of the strength of our evidence against the null hypothesis. As a measure of strength, it works inversely. The closer to zero, the stronger the evidence against the null hypothesis. The p-value is defined as a conditional probability. It is the probability of getting a result as extreme as or more extreme than our observation, given that the null hypothesis is true. And the level of tolerance that the student spoke about is what we call the significance level. It is the number that we use to compare the p-value to. If the p-value is lower than the significance level, we consider the evidence strong enough and we reject the null hypothesis. Some common significance levels are 0.05, 0.01, and 0.001. The most common is 0.05 or 5%. With these ideas in mind, we can answer letter C. Scenario C provides sufficient evidence that the coin is loaded in favor of heads because its p-value is 0.028, which is less than the common significance level of 0.05. Letter E. Does the outcome in scenario C prove that the coin is loaded in favor of heads? What about scenario B? In scenario C, the answer is clearly no. If the coin is fair, every once in a while we would see an outcome like this, so maybe this is one of those times. In scenario B, it is tempting to say that this proves that the coin favors heads. Otherwise, this would be like winning the lottery buying only one ticket. But we don't want to talk in terms of proving or guaranteeing. Here I wrote, neither of those outcomes categorically proves that the coin is loaded in favor of heads. Scenario B seems to prove it beyond any reasonable doubt, but we are always exposed to error type 1. Error type 1 is rejecting the null hypothesis when it is true. The smaller the p-value, the more unlikely it is that we are making error type 1. Here we can reject the null hypothesis very confidently. Here we reject it, but with some reservations. Here we don't reject it. In a hypothesis test, the probability of committing error type 1 equals the level of significance. This means that if we use the common 0.05 significance level, we assume that a true null hypothesis will be considered false and will be rejected 5% of the time. Letter F is the other side of the coin. Does the outcome in scenario A prove that the coin is fair? The answer is more clear. No. The fact that we fail to reject the null hypothesis does not prove that it is true. We are always exposed to error type 2. Error type 2 is not rejecting the null hypothesis when it is false. The probability of committing error type 2 is hard to calculate, but it increases as the significant level decreases. This means that by reducing the risk of error type 1, we increase the risk of error type 2 and vice versa. Here a last question. Would the outcome in scenario C be sufficient to infer that the coin is loaded at a 0.01 significance level? No, because the p-value associated to scenario C is 0.028, which is greater than the significance level of 0.01. That's why we say that the significance level shall be selected at the beginning of the study before picking the sample. Otherwise, you could be influenced by your personal wishes. For example, if you prefer to reject this null hypothesis, you could say, I'm going to use a significance level of 0.05. And if you prefer not to reject it, you could say, I'm going to use a 0.01. In this way, I don't have sufficient evidence to reject the null hypothesis. The same applies to the hypotheses themselves. Ideally, you should select them at the beginning of the study before picking your sample or collecting the rest of the information. The use of one significance level or another is maybe the most arbitrary and controversial part of hypothesis testing. I will speak about this and other issues at the end of this chapter. If you have understood these concepts, you are ready to test hypotheses in relation to the parameter proportion in a population. In this context of a proportion in a population, the normal model is more commonly used than the binomial model. We'll see all this in the second part of this class.